Welcome to this series of Specialist Maths, Chapter 3, which is Circular Functions. So in Chapter 3, we'll be learning about three new reciprocal functions, which are called cosecant, secant, and cotangent, respectively. But before we get into that particular topic, let's quickly review some of our more basic trigonometry. So this is what we know from trigonometry from previous years. You take a unit circle, which is simply a circle of radius 1, and any point on the circumference, let's call it point P, is basically denoted by cos, sine. In other words, what that means is the x value of any point is the cosine of the angle, and the y value of that same point is simply the sine of that angle. So as you can see, as the angle increases, it kind of starts down at 0, and it increases, it goes all the way up to 90, and then it keeps going all the way to 180, etc. You can do a full revolution. As the point rotates, what you see is that the height, which is the y value, starts increasing. So the value of sine increases, and the value of x, which is cos, that decreases. And that is basically what sine and cos do. Tan is somewhat related to those numbers as well, but we don't need to worry about that for the moment. So what this unit circle also does very well is something called symmetry. So I'll give you a very simple example of that, just to rehash your memory. If you go back to, let's say, exactly 30 degrees, let's try. Here we go. So at 30 degrees, you can see that the height of the point is 0.5. In other words, the sine of 30 degrees equals 0.5. Now, there is another point on the unit circle that has the same y value. Let's see what that is. If I keep going and I bring the green number to 0.5, here we go at 150. So the sine of 150 degrees is also 0.5. So what that means is there are multiple angles. In this particular case, there's two angles, 30 degrees and 150 degrees, at least in one revolution, that give you a sine value of 0.5. So that is just a basic overview as to how trigonometry works in the unit circle. Okay, so going back to this one here are the exact values. So we have the unit circle, but the unit circle is not just a pretty picture, it also gives us some nice values for sine, cos, and tan. And really, if you look at this picture here, it's just a whole listing of a whole bunch of coordinates. So for example, if you look at this one here, that is root 3 on 2 comma half. In other words, the cos of 30 degrees, or pi on 6 radians, is root 3 on 2, and the sine of 30 degrees and pi on 2 radians is a half. And you can go all the way around the unit circle. You can literally take an entire journey around it, and that journey will bring you back to the start, and you keep repeating the same coordinates over and over again. Furthermore, this is what we call our exact value table. So the exact value table is simply a listing of a whole bunch of exact values that we need to be familiar with. So these values are very important to know. Some people learn it via the special triangles. Some people just learn the table off by heart. It doesn't really matter which way you do it, as long as you are aware. For example, if I ask you what cos of 45 degrees is, you should be able to say it's 1 on root 2 straight away. Okay, so those are the exact values over there. The next bit of business really is this thing called symmetry, which I've already talked about just before. However, I think it's a good idea to just recap some of the rules that we've got going on. So we have something called the cast diagram. We call it either the cast diagram, or sometimes you can even call it the ASTC diagram. So I prefer sometimes saying ASTC, and the reason behind that is quite simple, because ASTC could stand for all students take calculus, or all stations to Caulfield, all stations to City, etc. Whatever works well for you, you can use that. Right. So let's get down to some basic symmetry rules, and then we'll jump into doing some sec, cosec, and cot. Okay, so in the first quadrant, we have this angle theta. So I'll just circle that theta over there. So that is in the first quadrant. of course x is cos and y is sine. So if you go to the second quadrant where the angle is pi minus theta, so this is what the line would look like. In other words, to get from the 0 angle all the way to that angle, we basically have pi minus theta is our angle. And as we saw on the calculator diagram before, that angle right there gives us the same sine value as the first quadrant. In other words, sine of pi minus theta is just sine of theta. Now, what happens with cos? Well, remember cos is the x value of the point. So here's our point right there. So in the second quadrant, the cos value is now going to be negative of what it was in the first quadrant. Okay, so in the second quadrant, cos of pi minus theta is simply negative cos of theta. And in a similar fashion, tan is going to be negative tan of theta. Right, so in the second quadrant, sine is positive and both cos and tan are negative. That's where the S comes from. That's the ASTC going on. Okay, let's go to the third quadrant. What's going on in the third quadrant? Well, in the third quadrant, our angle is down here. So down here, this is what it looks like. As you can see, it's in the third quadrant. It's in the third quadrant where both x and y are negative. In other words, sine of pi plus theta is just negative sine of theta. Cos of pi plus theta is negative cos of theta. And tan of pi plus theta, well, that's in the third quadrant where tan is actually positive. And again, that's the t right there. That's the tan. Right, finally moving on to the fourth quadrant. So in the fourth quadrant, we've got sine of 2 pi minus theta. So in the fourth quadrant, this is the angle we've got. So let's try and draw that as a arrow. Start here, go all the way around, and that's where we are. So that is 2 pi minus theta. So in the fourth quadrant, sine is going to be negative. So it's negative sine of theta. Let's just fix that up a little bit. There we go. Cos is going to be positive. So we have cos of theta. And finally, tan is going to be negative as well. Right? So again, that is the exact same idea that is done from ASTC. And there we go. Cos is the only positive in the fourth quadrant. Okay, so you can of course learn all the different, you can look at this diagram here and learn every single coordinate, or you can just learn symmetry. Okay, so if you learn symmetry, this is what's going to happen. You can either just put everything in the CAS, or you can memorize the special triangles, or memorize the exact value table, or you can memorize the entire unit circle. It's up to you, but I would strongly recommend just using symmetry. It's much, much better. Okay, so moving on, here we are with chapter 3, finally. So we've already learned some trigonometry in chapter 11, some of which I've taken you through already. So what we're going to do over here is we're going to focus on these reciprocal functions called Cosec, Sec, and Cot. They are respectively the reciprocals of sine, cos, and tan. Okay, so how does this really work? Well, all you got to do is remember, look at the third letter of each of the functions. So what I mean by that is you look at the third letter in green. So you look at cosec, the third letter is S, that is 1 over sine, the reciprocal of sine. If you look at sec, the third letter is C, that's the reciprocal of cosine. And finally cot, the third letter is T, and that is just the reciprocal of tan. Okay, so if you ever get confused, just look at the function, look at the third letter, and that will tell you which original function it is related to. Right, so without any further ado, let's jump into our examples. And I've got a little unit circle here as well to help us with some symmetry. So, question 1a. Evaluate each of the following in exact form. So we have sec of 5 pi on 3. So first things first, we need to relate it back to the original circular function. The third letter is C, so it's 1 over cos of 5 pi over 3. Right, so that's the first step to do, just relate sec back to cos. Once that is done, we're then going to use some symmetry. So 5 pi on 3, this is something you should have known from your 11 studies. 5 pi on 3 is basically 2 pi minus pi over 3. And why that's useful? Well, the way we can use this is we could say, well, we start at 0 and swing all the way around to 2 pi. So that's 2 pi right there. And then you go backwards by pi on 3. And you end up on this line right here. Clearly, as you can see on that line, we are in the fourth quadrant. And in the fourth quadrant, cos maintains its positive value. So what that means is cos of 2 pi minus pi on 3 really is just cos of pi on 3. And if you look back at the exact value table, or from your memory, cos of pi on 3 is just a half. And when you take 1 and divide it by half, you end up with 2. And that right there is our answer. Okay, so that's all you got to do. 2 is the answer for sec of 5 pi on 3. If you'd like to verify that on the CAS, you certainly can. I'll just create a new document to take it from there. So calculator. Now my calculator is in degrees. I'm going to change that to radians. Yours should be in radians. I'll go to trig and let's go to sec and then create a fraction. And then 5, and then pi, click the pi, go back to 5, and then 3 on the bottom, and there we go. Sec of 5 pi on 3 is 2. Awesome, so that works out, and now you can see that it certainly does work very well. Okay, moving on to the next one, cot of 17 pi on 6. So cot of 17 pi on 6, well, the third letter is t, so we're going to relate this one back to tan. Alright, so cot of 17 pi on 6, that's going to be 1 over tan of 17 pi over 6. Cool. So what is 17 pi on 6? Well, 17 pi on 6 is simply 3 pi minus pi on 6. So 3 pi minus pi on 6. Okay, so tan of 3 pi minus pi on 6, let's look at what 3 pi is. So I've already done a 2 pi rotation there. 3 pi just takes it one more further. And then when you go backwards by pi on 6, you're looking at an angle that looks something like this. So we are in the second quadrant, and in the second quadrant, tan is negative. So that's negative tan of pi on 6. Right, so now what we need to do is know what tan of pi on 6 is. Now, tan of pi on 6 is just 1 over root 3. So negative tan pi on 6 is negative 1 on root 3. Of course, flipping that, we end up with negative root 3. And there you go. That is our answer. You can, of course, verify that on the calculator as well. So the answer to cot of 17 pi on 6 is simply negative root 3. Right, jumping on to the final example for question 1, cosec of 7 pi on 4. So the third letter is S, which means we're looking at sine. So here we're looking at 1 over sine of 7 pi over 4. Right, so again, what is 7 pi on 4? 7 pi on 4 is simply 2 pi minus pi over 4. So again, looking at the unit circle, 2 pi again brings us all the way to the same x-axis, the positive x-axis. And going backwards by pi on 4 gets us right there between the two quadrants. Let's try that once more. That's more like it. There we go. That looks like a 45-degree angle. So we're down all the way here. And again, that is in the fourth quadrant in which sine is negative. So that's 1 over negative sine of pi over 4. And sine of pi on 4 from the exact value table or special triangles is 1 on root 2. So that's 1 over negative 1 on root 2, or in simpler terms, just negative root 2. And there we go. That is our answer. Okay, so now that that is done, that is how you evaluate any reciprocal function of any angle. You simply use symmetry to get you around the unit circle to determine whether you've got positive or negative, and make sure that you're looking at the third letter to see whether you're looking at cos, sine, or tan, respectively. Right, so now let's look at a couple of other ones that are slightly more challenging because of the presence of a negative on the angle. So first one, we've got a cosec, but this time it's cosec of negative pi on 3. So let's see how we can deal with this. So again, the first thing you want to be doing is converting it into sine. So cosec converts over to sine. So cosec of negative pi on 3 is simply 1 over sine of negative pi on 3. Now if you remember, one of your other exact value symmetry properties is that sine of a negative angle just takes the negative outside. So sine of negative pi on 3 is just negative sine of pi on 3. Okay, now that that's done, we know that sine of pi on 3 is root 3 over 2. So 1 over negative root 3 over 2 is negative 2 on root 3. And just for completeness, let's go ahead and write that in rationalized form. It will be negative 2 root 3 all over 3. And there you go. That is our answer. Again, feel free to use your CAS to double check these results. Okay, so now that that's done, let's move over to the final evaluating question. Cot of negative 11 pi on 4. So cot, this one, the third letter is t, so we're looking at tan. 1 over tan of negative 11 pi over 4. Now fortunately for us, tan works with negative angles the same way that sine does, and that is, it throws negatives out the front. So that negative that's inside the tan will simply jump out the front, and we end up with negative tan of 11 pi on 4. So we need to now work out how do we get tan of 11 pi on 4. So I'll keep the negative. I might actually chuck it to the top to make it a bit easier. Negative 1 over tan. Now 11 pi on 4 should be 3 pi minus pi on 4, because that's just 12 pi on 4 minus pi on 4, and that's 11 pi on 4. Okay, now 3 pi minus pi on 4, let's use our unit circle here. Start at 0, 1 pi, 2 pi, 3 pi, and then go backwards by pi on 4. So we are in the second quadrant. Now, in the second quadrant, tan is actually negative. So this is negative 1 over negative tan of pi on 4. In other words, these negatives actually just cancel out. So you just end up with 1 over tan of pi on 4. And fortunately for us, tan of pi on 4 is just 1. So 1 over 1, and our answer is a nice, beautiful, easy 1. Alright, so that is how you work with negative angles when you're dealing with your reciprocal circular functions. Right, so that's how that one works out. Okay, so sometimes you might be a bit scared to do some of these questions from scratch. So you can say, okay, you want to use symmetry to find it, and you might feel like you want to use your CAS. Then you realize that you're just in degrees mode, and then you stuff it up anyway. So if you are using your CAS to work out these values, just make sure that you are in radians mode. Okay? Cool. So now let's jump on to the Pythagorean identity. Okay, so this is the second part of what 3a is. There's 3 parts. There's evaluating the Pythagorean identity, and then finally graphing. So the Pythagorean identity is simply a relationship that is from the unit circle itself. So what I mean is, if you draw a unit circle, I'll draw a rough idea here. Okay, so here is a unit circle, and if you draw any angle, you basically get the triangle inside there. So your triangle extends all the way to the circle. The height of the triangle is sine theta. The width of it is cos, and the radius is always 1, because remember, this is a unit circle. So if you apply Pythagoras' theorem to this, you take the bottom squared, which is cos squared, you take the height squared, which is sine squared, and that should equal 1 squared. In other words, cos squared plus sine squared will always equal 1, as long as you are using the same angle. So that is the basic Pythagorean identity, which you need to start getting familiar with. But sometimes there is also a need to use what we call the two modified versions. So if you take this Pythag identity, and then you divide both sides by cos squared, what ends up happening is you end up with 1 plus tan squared is equal to sec squared. So that's what we call the modified Pythag identity number 1. In a similar way, you can take the same identity and divide both sides by sine squared theta. What you end up with is cot squared plus 1 equals cosec squared. The good news is that these, I believe, are on the formula sheet, so you don't need to memorize them. If you feel like you need to derive them from first principles each time, that is okay. Just make sure you know this one very well off the top of your head, and then the other two can be derived quite easily. Okay, so now that that's done, just make sure that once you know all these different identities, you must make sure that you protect yourself from identity theft, because if you don't, then you could be in trouble. Okay, so let's jump on to our examples. Right, so our first example is this one here. We know that x is an angle that is somewhere in the second quadrant. So pi and 2 to pi, that's 90 degrees to 180 degrees. That is an angle somewhere in the second quadrant. We also told that cos x equals negative 3 on 5. So that is a further reassurance that cos is negative in the second quadrant, because we have a negative value of cos. So this question is asking us to find three things: the exact values of sine, cot, and sec. Now, one thing you need to be very aware of with these questions is that you are not necessarily going to find the values of sine, cot, or sec via the angles. So we're not going to worry about what the actual angle is. We're just going to simply convert from cos to sine, etc., etc. And here's the best way to do it. You simply draw just a normal Cartesian axis that would normally house your unit circle, and simply draw a line that represents where your angle is. So x is an angle that is here in the second quadrant. Now, what we need to do is, we know that x is this angle right there, so I'm just going to define that as x. But what we can do, just to make our life a bit simpler, is we're going to take this triangle. I'm going to just highlight that for you. This triangle that is being formed, and I'm going to draw it again. I'm going to draw it again. This time I'm going to call that theta, and let's now put in the value of cos. Now, cos is negative 3 on 5, so if you remember your SOHCAHTOA, cos is adjacent over hypotenuse. So we've got a hypotenuse of 5 and an adjacent of 3. Now, one thing you also need to know is that a very common Pythagorean triple is what we call the 3, 4, 5 triangle. So if you know that your hypotenuse is 5 and one of your shorter sides is 3, automatically the other side is going to be 4. You can also double check that by checking 5 squared equals 3 squared plus 4 squared. It gets you, that is something that certainly works. Okay, now what we can do is we can say, well, I know that I've got my full triangle here. Well, what is sine? Let's go ahead and use SOHCAHTOA again. Sine theta is going to be, so I'm going to use theta this time. Sine theta is opposite over hypotenuse. So opposite is 4, hypotenuse is 5. So that is using this triangle here. So I'm just going to circle that triangle. This triangle leads to this factor here. But we don't want sine of theta, we want sine of x. So luckily for us, we know that x is in the second quadrant. So we could say, therefore, sine x would be the same thing, would be 4 and 5, as x is in quadrant 2. Okay, so if we were in the third or the fourth quadrants, for example, then we would say sine x equals negative 4 and 5. So basically what you got to do is use the theta triangle, this green highlighted one over there, use that triangle to get just the value of the fraction, and then use the quadrant that x exists within to get the sign of it. And when I say sign, I mean positive or negative. Right, so now let's look at cot. So what I'm going to do for this one is I'm simply going to say cot of x is going to be 1 over tan. And we know that tan is really just sine over cos. So 1 over tan is going to be cos over sine. So the way we can deal with that is, well, we know cos x is neg 3 on 5. So that's on the numerator. Sine x we just got from part A, which is 4 on 5. So neg 3 on 5 divided by 4 on 5, well, that's just negative 3 on 4. Okay, so let's just double check. We are in the second quadrant. In the second quadrant, tan is negative, and therefore cot will also be negative. Cool. I'm pretty happy with that as the answer. Finally, let's go to sec of x. So sec of x is going to equal 1 over cos. Recall that you want to look at the third letter. So sec is 1 over cos. We know that cos from the original question is neg 3 on 5. So 1 over neg 3 on 5 is just negative 5 on 3. And there we go. Your job is done. Okay, so that brings us to the end of using the Pythagorean identity to swap from one ratio to the other. Now let's go to our very final two questions. And here we are. So with these final two questions, sometimes things can be a bit tricky. Right now, up until this point, most of us would think, yep, cool, trigonometry is very fine. It's a good topic. It works very well. And then suddenly, before you know it, a question comes along that says, simplify this monstrosity of an expression. So you do have to be a bit careful with some of these. They do rely very heavily on the Pythagorean identity. So you have to exercise a lot of caution when dealing with them. All right, so 4a, here we go. So it says simplify the following: 1 over 1 plus sine plus 1 over 1 minus sine. Okay, normally when you're adding two fractions together, it's always a good idea to bundle it together into a single fraction. So let's go ahead and do that. So I'm going to create a nice big fraction vinculum right there. And 1 plus sine multiplied by 1 minus sine is going to be our new denominator. So 1 plus sine times 1 minus sine. So to get the numerator, we're going to simply do what we call our usual favorite cross multiply. So 1 minus sine multiplied by 1 is of course just 1 minus sine, plus 1 plus sine multiplied by 1 is of course 1 plus sine. And look what's happening over here. I have a negative sign and a positive sign. So they certainly cancel out, and we just end up with 1 plus 1 on the numerator. 1 plus 1 is of course just 2. Now on the denominator, I have 1 plus sine multiplied by 1 minus sine. Well, 1 plus sine times 1 minus sine, that really is just 1 squared minus sine squared. So I'll mention where that comes from. 1 squared minus sine squared. So that right there, that is simply our difference of two squares formula. So if you have a plus b, a minus b, that is just a squared minus b squared. So here our a was 1 and b was sine. So a squared is 1 squared minus b squared, which is sine squared. And if you look back at the Pythagorean identity, if you look at this one, cos squared plus sine squared equals 1. If you take the sine squared over to the other side, you end up with 1 minus sine squared, which happens to be just cos squared. Okay, so what that means is we just have 2 over cos squared of theta. Now, if 1 over cos is sec, then 1 over cos squared is just sec squared. So what that means is the 2 remains where it is, and the cos squared at the bottom jumps to the top and becomes sec squared of theta. So what that means is the simplification of 1 plus sine, or 1 over 1 plus sine, plus 1 over 1 minus sine, is just 2 sec squared of theta. Awesome, now we're at the very final last one. Okay, so we've got 1 minus sine squared times 1 plus tan squared. Well, the good news is that 1 minus sine squared, we kind of already saw it on the previous question. 1 minus sine squared, that is just cos squared. So let's simplify that first, because that's an easy one to do. Cos squared theta. Now, 1 plus tan squared, I wonder if that comes from somewhere else. Let's go back to our modified identities. Oh, and what do you know? 1 plus tan squared is actually sec squared. So I'm going to write that as sec squared theta over here. Right, now what you might notice is that I've got cos squared theta, sec squared, well that's just 1 over cos squared. So what we've ended up now with is a cos squared divided by cos squared, which just happens to be 1. So what that tells us is that you can choose any angle you want, and if you evaluate 1 minus sine squared off that angle, multiplied by 1 plus tan squared off that same angle, you just end up with 1. And that will be the case for any angle you choose, whether positive, negative, acute, obtuse, whatever, it doesn't really matter. Excellent. I hope all those examples and the notes made sense. If not, then please do let me know. Or otherwise, you can straight away get to the exercise. Have a go at the relevant questions from exercise 3a, and I will see you in the next video where we look at graphs of sec, cosec, and cot. Catch you later. Bye-bye.